It was a day like another in Swindon. I was oblivious of what was going to happen. I walked to the basement to test an IBM XT. The PSU worked fine. But then, I went to test the motherboard.
In 3, 2, 1, go.
Hello and welcome back to my channel. That was an interesting day indeed, and sorry for the cinematic intro, it must be because I work in that industry. Indeed, there is an IBM XT on the bench today. I ended up taking it home because of what happened when I tried to power up the motherboard.
In 3, 2, 1, go.
Yes, you guessed it. That's the usual tantalum capacitor on the 12 volts line, so maybe it's better to replace them all rather than wait for more fireworks, and there will be more fireworks, so stay tuned. Now, this is an IBM XT 5160, it's the successor of the 5150, which was launched in 1981. This is from 1983, at least it was launched in 1983, and it sports an Intel 8088 CPU, which runs at 4.77 MHz. I understand that depending on the motherboard that is fitted inside this unit, you can have something in between 128 and 640 kilobytes of RAM. Now, this is the predecessor of the PS2 line. And you've seen this PS2 on this channel on this video, and I've been restoring and repairing this one. It's not ready yet. I've got all parts of this computer scattered around my shop here, but I'm getting there and you'll see a video at some point about this. So that's the PS2 that was released in 1987, which is more or less when the XT 5160 was discontinued. Now, I couldn't really test much of this XT when I was at the museum, so the idea would be to open it up, remove all the boards, remove the motherboard, replace the tantalum, and at that point test it, see whether it's working or not, and then we can move a step at a time and test the floppy drive, the hard drive, and the number of boards there are inside this unit. So enough me talking, let's open it up and see what we can do for it. Right, here we are. Let me start with saying that this is my first IBM XT. I'm really not familiar with this machine. I do see there's a hard drive here. It says Type 13 20 megabyte. It's branded IBM. So hopefully this is one of those squeaky hard drives from these old IBM machines. I really love the sound of it. We have the massive power supply, which is probably no more than like 70 watts or more or less. We have a 5 1/4 floppy drive, which looks like in decent condition. And then we have 7 cards attached to this motherboard. And from what I can see, some of them are like expected. We have a video card, we have a controller for the hard drive, we have a controller for the floppy drive, and might be a parallel port. We'll take a look in a minute. But I also see a board which I've only seen online on Adrian's Digital Basements channel, which is a board with a hard drive attached to it. And I'll have to educate myself and find out how it works. So let's start by removing everything here. So card number 1 is a simple parallel card, and it's got a parallel port at the back. Card number 2 says async card, and this is just basically a serial adapter, so that's the serial port at the back. Card number 3 is the floppy controller card. It comes with an edge connector at the back for the floppy, internal floppy, and I'm guessing that this is for an external floppy if required. Card number 3 is the hard drive controller, and there should be an MFM card, and I understand that this is revision number 3 of this type of controller, released in around 1986. Card number 5 is a network interface adapter. I can't really find much about this card. It comes with a BNC connector at the back. Card number 6 is the interesting one in my opinion. It's a Plus HardCard 20. This is a 20 megabyte hard drive, very thin for the time, onto a card. So the idea is that Quantum decided to develop this card as an easy way for the user to just install a hard drive into a computer. You didn't have to disassemble anything. And remember that these computers didn't really have space for additional hard drives, so you had to remove the existing one, probably reinstall everything. That was just a card that fits into the computer. I'm not sure how it works. I'll have to find out. I'll have to probably watch the Adrian's Digital Basement video again. But it's impressive that this was released in June 1986. And this is the very first 1-inch thick hard drive. Again, we're talking about 1986. This is very impressive. So I will be very happy if this worked. And card number 7, it's a Paradise EGA video card. It comes with an EGA connector here. This is not composite, as you might think. That would be too easy. And I happen to have more or less an identical one. It's still a Paradise. It has a few minor differences, but it's more or less the same card. The thing is, I don't have an EGA monitor, but I purchased an adapter, so hopefully we can see the output of this video card through my capture device. I still have to assemble it and program it, so maybe it's something we can do in this video. Right, that's it with the cards. Next would be the motherboard. Motherboard is out, everything is pretty dirty, so I think I'll take these opportunities just to vacuum the case. The motherboard, I'll have to be a bit more careful. I can't just vacuum the motherboard, as I would probably need like some anti-static brush or something. But yeah, I'll see what I can do to get rid of these dust. Right, here we got the board. So what I'm going to do first, I'm going to replace the tantalum capacitors on the plus 12 volts and the minus 12 volts. This capacitor here is the one which exploded. I've removed it already. And as you can see, these are the very old version with 3 legs. You can't really find tantalum or any capacitors with 3 legs. But the thing is, the outer legs are the same thing. They're shorted. I need to find out which one is plus, which one is minus. These are all decoupling capacitors, and I can just replace them with good quality electrolytic capacitors. For the minus 12 line, I think we have this fella here, even though it doesn't say anything, but a C57 here, so I'm assuming that's C58, which is another 10 microfarad tantalum, and I'm definitely going to remove this one because that's very prone to exploding. And if I'm looking at the 5 volts line, I thought I didn't want to do anything, but again, there are not so many 10 microfarad tantalum capacitors. I believe these are these 1, 2, 3, 4, probably these 2 here, these 2 chunky here, and I think it's 1, 2, 3, 4 here on the memory banks. It's not too many. I would say let's get rid of all of them, just in case, even though I suspect the 5 volt is probably not as critical as the 12 volts. What do you think about it? Leave a comment down below, because honestly, I don't know, so I'd love to hear what you have to say. For these capacitors, I should have some Panasonic ones, which should be like decent quality. So let me see what I got, and I'll start replacing these nasty tantalum exploding capacitors. Removing components from a motherboard with lots of ground planes can be challenging, and this was no exception. First, I tried with the desoldering gun, but that was not able to clear the holes. So I cut the capacitor with my cutter and tried to remove the legs. Even worse, those legs just refused to come out, and I took a long time to finally pull them out. Then I tried with some desoldering wick, but that did not work. I brought some hot air to help, but I was still unable to clear those holes, and the hot air was discolorating the PCB, which was scary, but the color would return to normal once cooled down. Still, I wasn't comfortable doing that on such an old board. I hoped that the one closest to the edge was going to be simpler, but no, same struggle. It took me a long time to remove the plus and minus 12 tantalums, and I was so nervous, as I could see the pads getting damaged the longer it took. But I did it. And finally, I soldered the electrolytics in their place. Right, change of plan. Removing those capacitors has been very difficult. Clearly there must be a thick ground plane on this board, and I do feel that insisting and keeping removing those capacitors is not worth, as this is a 40 years old board. It's fragile. I don't want to insist. I feel I might be causing some damage if I keep insisting. So I think it's totally fine. I have removed the 12 volts, the plus and minus 12 volts, and I think a few plus 5 and maybe one minus 5. I think this is going to be totally fine. So let's get the power supply back up and I'll quickly test it, make sure it still works. And then we can try and power this up and see how it goes. What can I say? I'll wear some safety goggles. Now, if you have a method to remove capacitors or components from a board like this where you have a thick ground plane, please do let me know down below in the comments. I'm very curious because again, as it is, I don't really have a consistent method that works on every single board. Ideally, I'd like not to throw too much heat at any given board. Obviously a 40 years old board, it's even more sensitive than anything. So please do let me know if you have anything that might help. Let's get the power supply out. Okay, let's quickly test the power supply. I tested it before, but you know, let's just do that again real quick. Let's power up in 3, 2, 1, go. Yeah, 5 volts is fine. It's no load, so obviously voltages are a bit weird, but that's fine. 12 volts is again no load, so that should be fine. The minus 12, which is a bit weird again. This I don't know what it is. Power okay, something like that. And then that should be minus 5, which is minus 5. So yeah, everything seems to be perfectly fine. This video is sponsored by PCBWay. PCBWay offers PCB manufacturing for all your electronic needs. The service is very easy to use. Just go to PCBWay.com and upload the Gerber file of your project. The system will prepare it automatically, but you can tweak the parameters yourself. There are plenty of shipping options to suit your needs. I used PCBWay for some previous projects and I was really impressed by the manufacturing quality. This XT-ID card would work perfectly in this machine. The link is down below in the description. Thank you PCBWay for helping the channel, and now let's go back to the IBM. Okay, well I think I'm ready to go. Power supply is connected to the motherboard and the multimeter is monitoring the 12 volts line, so we can see what happens there. I'm ready to go, so let's see what happens. In 3, 2, 1, go. No bangs, got 12 volts. Yay! We got life out of this board. I got the speaker connected and the speaker said, "Hi," which means the board is posting, I suppose. Okay, whew. No more fireworks. Also, as expected, I'm noticing that with the board in place, the voltages are totally fine. 12 volts has become exactly 12 volts. 5 volts is more or less 5.0. It's pretty normal for those old power supplies to have kind of inaccurate voltages without a load. Right, we know this board is doing something, it's definitely posting, and the next step would be to plug the video card and see whether we get a video output. Now, when I first tested this motherboard, when the tantalum exploded, I removed the tantalum and I went ahead and I plugged the video card, because the thing is, these tantalum capacitors are just filtering capacitors, so you can remove one temporarily and, you know, it's not the end of the world, it should work for a quick test. Now, when I went ahead and plugged this video card into the board and powered up, this happened. In 3, 2, 1, go. Oh. It's failing. In 3, 2, 1, go. Oh. And yes, there was another explosion, and you guessed that right, another tantalum capacitor. In this case, it was this tantalum capacitor here, which I have removed already. Now I can see on the board there are 1, 2, 3, 4, 5, and 6 with the one removed tantalum capacitors. So I'll have to just do buzz the capacitors and see on which lines they are. And let's remove the ones which are on the plus and minus 12 volts. On this side of the board, the 12 volts and minus 12 are coming through these vias here. One is plus 12, one is minus 12. So we can check. I would start with the one which I removed, which I know it's on the plus 12 volts line. So this is obviously to be replaced. Okay, this is probably on the minus 12. Probably this one is on plus 5, as is this one. as is this one, and as is this one. So obviously these are on +5, this is on -12, and this is on +12. So I'm going to remove these two only, and then hopefully we can test this video card and hopefully won't explode on us. For the video card, as you can see, I went with the largest tip I have, but that was not really necessary. The tantalum came off with no struggle, which is good for a change. Alright, video card is in. Now before I plug a display or a capture device, I just want to do a dry run and make sure that nothing explodes and the computer is still beeping with the card installed. In 3, 2, 1, go. No bangs again. And we do have a beep, so that is great news. Now my next problem is, this is an EGA card and there's a very limited amount of VGA, 8-bit VGA cards which fit on this computer. I haven't got any of them. So I decided to buy these. It's the RGB to HDMI adapter and it's based on a Raspberry Pi and this little CPLD board which sandwiches on the Raspberry Pi. Now I've just purchased this, I've never tested it myself, and most importantly I need to put this together. And also I need to insert an SD card with the software on it, and then hopefully we have a picture out of this thing. So let's put this together real quick, and then we can program it, and then we can test it. Okay, the RGB to HDMI should be good to go. I got an SD card in it with the latest software. This is the first time I'm powering it up, and I understand I should see some screens when I power up, so it doesn't really matter whether I've got an EGA input or not. So let's power up the Pi now. Yeah, if I give power to the power supply, that might work. So let's power it up now. Oh, okay, I have a light in there, but I haven't got any video output. And we're in. I have selected the appropriate firmware, and there is a profile, a pre-made profile for the IBM, or actually for the EGA. So that should be ready to go. Let's reassemble the IBM and see whether there's a picture coming out of it. Right, this is the moment of truth. I've got everything connected. I'm using what I think is a serial cable with the gender changer here, and the RGB to HDMI is connected. It's just waiting for sync. And I also have a very heavy keyboard connected to the IBM, just in case we get something out of it. I feel optimistic, let's put it that way, because it was beeping, and I think it's time to power up. Okay, in 3, 2, 1, go. Okay, well, I need to... is it? Oh, it's working! I don't know what that was. But it's definitely working, look at that. It's checking the memory. And the board here, I forgot to mention, it says 256 640. So that potentially is 640, and it looks like it is. And it's working. We got error 601. 601, like the PS2, should be floppy missing, which is missing. There's nothing connected to it. And what happens if I press F1? It goes into basic, I suppose. Doesn't do anything. Well, either there's an issue with the keyboard, or I'm not sure, but I would expect something to happen when I press F1, and nothing seems to be happening. So maybe I can try some contact cleaner in the keyboard connector and inspect it as well. And no, the contact cleaner didn't help. I'm pretty confident that by pressing F1, it should go at least into basic. At least if it's like the PS2. I'll take a look at the keyboard, and then, I can also take a look at the motherboard section, end of the keyboard, but then I might need another keyboard just to test. Right, so I've opened the keyboard and there's a little PCB here with a little controller. Now I've looked into the datasheet of this controller, and what this controller is doing is basically encoding the matrix of the keys being hit on the keyboard itself, and it's sending a binary code which is matching the key that you pressed on the keyboard itself to the motherboard. The keyboard here is getting 4 wires. You got ground, you got 5 volts, then you got clock and data. I've checked 5 volts, 5 volts is fine. So I started looking into data sheets and how this keyboard works. And most importantly, I wanted to know whether something is going back to the keyboard, and if something is going back to the keyboard, whether it's the right key or not. Now, being old technology, it's kind of easier to understand what happens. As I did in my previous video when I repaired the Macintosh SE, I think I'm able to scope the data line and see actually what key is being sent to the motherboard. So at that point I can hopefully ascertain whether there's an issue with the keyboard logic, or maybe the motherboard is not recording the logic for whatever reason. So I got the oscilloscope on screen, and let's see what happens when I press the key on the keyboard. There you go. I connected 2 channels here. Again, one is the clock, one is the actual data. Now, the purple line is the clock. It's basically telling the computer when to expect data from the keyboard itself. It's only setting the time, and that's why you have a constant waveform in there, more or less. The yellow line is the one that I'm interested in. It's our data being sent from the keyboard to the motherboard. I know it sounds complicated, but stay with me because it's pretty easy. So whenever a key is pressed, you will see that the purple line, I'm pressing different keys, the purple line stays the same because the clock is setting the time, it's always the same. But depending on the key I'm pressing, you have a different data going back to the motherboard. Now, the first 2 pulses, that's the start bit. That's telling the motherboard, I'm sending you some data. So we need to look at the remaining bits. And I understand the last 2 bits are always low for whatever reason. So let's do a quick test. Now, to find out what is the binary code of a specific key, you just need to look at the keyboard table we have here on the technical reference manual. You have a decimal number by every key of the keyboard. So for example, key number K is number 37. All you need to do is grab the Windows calculator and turn into the programmer mode. It's in your Windows, everybody has it. Now 37 in binary is 00100101. So let's see what happens when we hit the key. So let's see what happens when we hit the K key on the keyboard and see what happens on the oscilloscope. Now, when you're matching the binary code, you have to look at it the other way around. I think the reason is if you're looking at the oscilloscope, but the signals are coming from right to left, so that's how they're sent from the keyboard to the motherboard. So the first one that is being sent to the motherboard is on the left-hand side. So if I'm looking at my code the other way around, it's going to be 10100100, and if you're looking at the yellow trace and ignore the first 2 pulses, you have 10100100. So that's my K key, and I know that works. That's telling me that the keyboard is working, the logic is working, and I'm not sure whether the motherboard is getting that because I'm probing this on the keyboard itself. But what about the F1 key? Maybe there's something wrong with the F1 matrix. It's unlikely, but let's do the same logic with the F1 and see if that works. Now F1 on my table is 59, and 59 in binary is 00111011. And if I set the oscilloscope to wait for a signal and I hit the F1 button, this is what I'm getting. So I'm expecting, reading backwards, 11011100. Again, you start looking from the 3rd pulse, you have 11011100. So that's totally fine, and it looks like the keyboard is working fine, and it is sending the F1 key to the motherboard. So I would probably need to make sure that this is actually being detected by the motherboard, so I'll follow the signal into the motherboard and see if that works. Right, I'm back on the motherboard. I've removed the video card for the time being for what I need to do. I don't really need a motherboard. And looking at the schematics, I see that the keyboard data line is getting into this little IC here, which is an SN74LS322, and particularly on pin 17. So let's go pin 17 and see whether I see the same data which we observed on the keyboard itself. So this is my pin 17, and if I type some keys, ignore the purple line is disconnected. But yeah, I mean, I got different waveforms for different keys, and the F1 is also working. I'm tapping F1 now. Yeah, it looks like the signal is getting into the motherboard. So, you know, we don't have a trace issue or cable issue or some sort. Now, before I dig too much into this, I really would like to try and plug the floppy drive and see what happens with the floppy drive, just in case the motherboard is not designed to run without floppy drive. And without floppy drive, it just stops and it doesn't do anything. Okay, I've got the drive out of the case, it's connected to power, and the controller board is also ready to go in the motherboard. There are two tantalum capacitors here, but I did check it and they're on the 5 volts line, they're not on the 12 volts line. I don't see tantalums on the drive. Actually I see two small ones, but they're not on the 12 volts either. So let's plug the controller back in. And the video card is back as well. And the keyboard, of course, is connected, so we can test and see whether it's working or not. Well, I guess it's time to power up, so let's gear up and let's power up. In 3, 2, 1, go. Will the drive seek? It did. Oh, I guess the system is trying to boot from the drive because the spindle is moving. Ah, ooh, okay. Aha, the keyboard doesn't work. So we do have a problem with the keyboard. Okay, so we know that the keyboard data is getting into the keyboard because we found it on this IC. Another important signal coming out of this IC is the RRQ. It's an interrupt, which is basically telling the processor, hey, someone has hit the key on the keyboard, so the processor doesn't waste time scanning the keyboard if nobody is touching the keyboard. So one thing I want to check now is whether we have a signal coming out of this U27, which is just a shift register. If I understand correctly, it gets the serial data, which is coming from the keyboard in a serial way, and turns that into a parallel stream, which can go onto a bus somewhere else on the system. So I'm checking pin 1 of U27, and I'm supposed to see a pulse every time I'm hitting a key, and there's nothing coming out of it. So this is great news. And that explains what happens. If I understand correctly, the keyboard is sending data to the motherboard. It's just that the CPU is not being informed that someone is using the keyboard. So the data is being ignored, more or less. Now, another important signal coming into this IC is clock on pin 11, and that is basically telling the IC, okay, it's time to display the data on your outputs, because obviously I guess this is on a bus or something, but the data is not displayed all the time. Pin 11, we have, I would say, a very, very slow clock. It's a 9 Hz clock. Fair enough, this is a slow computer, but I don't think that's correct. We shouldn't see 9, we should see something a bit better than that. Now, if I follow pin 11 backwards, this is coming out of these U21, and that is a flip-flop. The flip-flop is getting the peripheral clock here on the left-hand side, is getting into pin 9. So my understanding is the peripheral clock is going into the flip-flop, the keyboard clock is going into the flip-flop, and the peripheral clock more or less synchronizes the keyboard clock, so the output is something which is compatible with the keyboard and the system at the same time. So the data output from the keyboard is clocked with what the system is expecting, more or less. I know this is not extremely clear, but that's my understanding. But what's important is we should see the peripheral clock on pin 9, so let's check that one. And we have a 2.3 megahertz, that's fine. The peripheral clock is supposed to be half of the main clock, which is 4.7, so that is totally fine. Now on pin 4, we should see the keyboard clock, which is the one we observed earlier on when we were deciphering the binary code coming from the keyboard. So let's check what we get on pin number 4. Well, unsurprisingly, we get that 9 Hz clock or signal. And this doesn't make any sense, because when I'm using the keyboard, There's really nothing changing, and we should see more or less the same clock that we observed earlier on. So now I'm wondering, we tested the keyboard clock on the keyboard itself yesterday. I think I did check for continuity to the plug of the keyboard and it was working, but I really never checked whether the signal was actually making it there. And so I think now it's a matter of, is the keyboard clock actually reaching the motherboard? Because as I see now, it doesn't seem so. And if the keyboard clock doesn't reach the motherboard, I guess that's why the keyboard data doesn't get listened to, because there's no clock to basically telling the ICs, hey, we got some data here. This is bit 0, bit 1, bit 2, bit 3. So I would say the next step would be to inspect the keyboard connector and start tracing things, start to understand what goes where. Okay, so the first thing I want to do is to check continuity between my clock line here and pin 4 of U21. It should be a direct link, and that will cover the connector here, the cable, the connector there, the traces on the motherboard, so that will tell us whether that's working or not. I'm in continuity mode, and let's check this out. Okay, we do have continuity, which is weird, so how is that even possible? So let's power this back up and see where the signal is stopping, but it shouldn't stop because there is continuity between the keyboard and the IC, which is supposed to read the clock, which we couldn't read before. Okay, I'm back on the keyboard and I have my sync on the keyboard here, so that's not a surprise. I don't know, let's check again U21. What? Wait. What? There is a clock now. What's going on? So U21 is now getting the keyboard clock. Does U26 get the oh yes, 66 kilohertz clock? And that is regardless of whether I'm using the keyboard or not. It was 9 hertz before. Most importantly, is the keyboard working now? It's working. I haven't done anything. Look at that, it's working. What? I haven't done anything. So does that mean we have maybe something intermittent? Maybe we have a solder joint which is not working well? I don't know. Oh, it stopped working. It stopped working. Okay, yes, we do have something, I would say, at the connector, because I touched the connector and this thing stopped working. There it is. Oh, God. It was just a connector. So I'm pushing it on to the right, and if I'm pushing it to the left, it's still working. And if I'm leaving it, it stops working. Look at that. This is so frustrating. It's just a connect. I did spray some contact cleaner in that. Okay, I'm giving up. Well, that's it for today. Thank you very much, and see you next time. No, I'm joking. Right, okay, let me inspect that connector, clean it a bit better, make it a bit more reliable, and I guess then we can move on. So it looks like there might be a fault with the cable event in the end. So I went back and checked continuity between the clock line and the pins here. There you go. You don't have continuity anymore. I'm bending the cable one direction, and this is the other direction. So yeah, there's a breakage in the cable itself, unfortunately. Yeah, which doesn't make things easy. Well, the good news is I just need another cable from a broken keyboard. This is swappable very easily, or I can just chop this off and install another one of these. I actually should have it. And I decided to replace the connector. I used a very good quality Rian connector, which I had for a Commodore 64. This had 2 extra pins, but all the others were in the right place, so I just saw them off. I'm pretty happy with the outcome though, a pretty solid result. Okay, it's all done. It looks great, by the way, and let's plug it up and we're ready to try. Moment of truth. Let me press F1 here. It's working. It's working! So that was the definition of overthinking, I guess. But I had fun and we learned a few things. I learned how this keyboard works. So we can now move on and try and boot something from this computer, and then we have many more boards to test. I think we've done enough for today, so I'm gonna pause the video here, and on the next episode we are going to continue with the floppy drive, the hard drive, the other hard drive, the remaining boards, and hopefully we can get to a point where the system is working reliably and is ready to go back to the Museum of Computing of Swindon, where it comes from. I hope you enjoyed this video. If you did, as usual, I'd really appreciate a thumb up down below, and also why not subscribing to this channel if you like this video and you would like to see more. Also, if I can ask you to leave a comment to hopefully tell the algorithm you like these videos and you'd like to see more like this. Well, that's it for today. Thanks for watching. I wish you a great day, and I hope to see you again soon here on this channel for part 2 and my next videos very soon. Thank you very much and goodbye. Bye bye.